Sometimes a single moment is enough to question an entire system, even it has been working flawlessly for hours before. Traffic sign recognition in our Škoda Enyaqs and Eldrocs is a good example of that. It is designed to detect which speed limit applies, and in at least 95% of all distances driven, the driver has the correct information available. Legally, only 90% would be required. But it is precisely those missing few percent that we remember. An unexpected deceleration, a sudden acceleration, and confidence is shaken. For the developers, this means acceptance is not determined by statistics, but by the experience in that one moment when the system reacts incorrectly. And with that, hello friends of the electrified charging fun and welcome to Electrified Speicher, your channel all around Škoda's e-mobility. In this video, I'll explain why such situations occur, how traffic sign recognition actually works, and where its technical and human limits lie. Let's get started. What your Škoda displays at the correct speed limit is not simply the result of a camera image. It is a decision based on several sources, and each of them carries its own uncertainty. The camera sees what is physically in front of it. The map knows what should apply according to the database. There are also legal standards per country and the vehicle's own position determined by GPS. An algorithm then merges all this information and derives a valid speed. You can imagine it as four people trying to agree on one number and somehow a decision must be made. There are priorities and predefined rules for this. In practice, that means legislative limits are always applied. Then, when the camera sees a sign, in most cases, this gets priority. If it doesn't, the map takes over. For predictive functions, for example, the vehicle slows down in advance before a curve or city boundary. Only the map is used here because the camera would see the sign way too late to react safely. From the user's perspective, this creates a paradox. We experience a system that appears certain of itself, yet its certainty is constantly calculated from uncertain sources. That uncertainty remains invisible until it becomes visible, for example, when the car brakes too early or too strongly. Psychologically, we don't react to the algorithm itself, but to the loss of control in that very moment. The display on the screen suggests certainty, but in reality it represents a probability statement, not more. And that explains why trust and transparency are so closely linked. As long as the car behaves in a way we can understand, we even accept small mistakes, like, yeah, I saw that wrong sign too, so it's fine for me. But once the logic becomes unclear, we perceive it as a threat. Especially when it no longer matches reality, even if it is technically correct from the algorithm's point of view. The camera in the vehicle is not an eye in the human sense. It doesn't see, it searches and interprets patterns. At present, it operates in grayscale. Colors play almost no role in recognition. What matters most is the shape of the sign, not its digits. The camera does not read speed numbers, there is no OCR, optical character recognition, involved. It captures an image and compares it to a pattern database. Therefore, grayscale increases the robustness of the system. A software algorithm then compares each captured image with learned patterns and looks for a structural match. If the structure fits a known template, well, that speed is adopted. So an 80 is not recognized as a number itself, but as a shape that looks like one. The neural network behind it was trained with millions of examples, not in the car, but on a dedicated server farm. The camera itself doesn't learn, it uses a fixed model. This means the recognition process is deterministic. It cannot learn that a construction site contains temporary signs, or that a dirty sign is only partially visible. It identifies whatever most closely matches the pattern it was trained on. In practice, the system can confirm a sign with confidence at a distance of up to some dozen meters. Earlier than that, it detects only contours and shapes, but only validates them once the probability is high enough that the object is truly a traffic sign. To us, this seems obvious until it goes wrong. If a truck has an 80 sticker on the rear tarpaulin, the camera may interpret it as a valid road sign because shape and contrast are nearly identical. The result is not a malfunction, but a correct conclusion based on incorrect input data. It depends entirely on the quality of the training and pattern data. The system reacts logically, but not rightly, and that distinction is essential. Technically correct and behaviorally right are not the same. The camera performs its tasks precisely, but the driving experience is defined not by logic, but by its effect in the very moment where it occurs. For these very reasons, the system doesn't rely solely on the camera. What the camera doesn't see is supplemented by the map. It is the system's secondary memory, if you want. The map data comes from a central provider, in Škoda's case the service provider HERE. HERE supplies many car manufacturers. It maintains a digital representation of the road network, with speed limits and intersections, road geometry and more. This data is updated once a month by Škoda and distributed online to the cars. Our ENIAC and LROC receive them automatically after verification and approval by the manufacturer. This creates an inevitable gap between reality and data. Sometimes the difference is only a few days, sometimes weeks or even months. The reasons are manifold. Behind the scenes, HERE processes a vast amount of data changes every week across Europe. Vehicles that detect a sign may send this information back anonymously. This forms a collective memory, a swarm constantly verifying whether the map still matches reality. Even so, the system has limits. A newly opened road may go unnoticed for a couple of days. A misplaced city sign can remain because correcting it provides little economic benefit. Not every modification or update is implemented, and errors in the data set can result. For the driver, that tiny discrepancy can make a huge difference. 20 meters earlier or later may decide whether the car brakes or not, and this could be the right point or the wrong point for you. The map is therefore not an absolute truth, but a probabilistically model filtered by economic and technical priorities, if you want to say so. For the user experience, that means we don't drive on a road, we drive on an interpretation of it. And errors in traffic sign recognition rarely stem from the technology itself, but from moments where reality and data briefly diverge. It often starts trivially, for example with a GPS dropout. If the system fails or shows even a minimal deviation, the vehicle may not know for a few seconds which section of road it's on. During that time, it estimates the nearest plausible segment. If that segment carries a different speed limit, the display and possibly the vehicle speed will jump. Another classic case, construction zones. New temporary signs are mounted maybe in places that the map doesn't yet include. The camera may not detect them correctly because of angle, light or placement, and the system cannot assign them reliably. Misinterpretations also occur through visual overlap. For instance, when a sign applies to a side road but stands where it can be seen from the main lane. Combined with GPS and map data, the system may consider it plausible. The algorithm behaves strictly logically, but the world it interprets is not logical. It's shaped by human diversity and disorder. In testing, this becomes clear. On a 750-kilometer journey between Switzerland and Czech Republic, I typically record 5 or 6 false recognitions, but in one extreme cases there were 37. And it is precisely this perception that defines our trust in the system, not the average, but the memory of the exception. Also, a speed limit is not a universal concept. It's a legal agreement, and every nation interprets it differently. What is an unambiguous sign in Germany can mean something else in Austria or in England or in Sweden. For example, in Switzerland, every town entry sign also has a speed limit sign. In Austria, it does not. In Germany, the city sign implies 50 kilometers an hour, even without showing a number. For humans, this is self-evident because we know the local system. But abroad, it already becomes harder, even for us. For a machine, it is an entirely different challenge. It must derive the meaning of the sign from shape, color, position, and map data specific to the country it's in and the context you are in when driving. The same applies to additional signs. Wet conditions or time restrictions or children playing are not fixed rules, but conditional situations. To know whether they apply, the car must interpret additional signals. For rain or time restrictions, the system evaluates vehicle, map and weather data. Even limits follow different national logics. In Germany, for example, the speed limit ends when you pass the city end sign. But in Austria, this is not the case if there was an explicit limited signal before. In the Czech Republic, every intersection you take counts as the previous speed limit. And that does not only apply to cities, but everywhere. This diversity is legally necessary, I guess, but technically risky. A pan-European system must know all these logics and apply them within milliseconds. The greater the variety, the harder true harmonization becomes. And as long as road signs have no uniform digital format, the street remains an analog data problem. There are two ways the vehicle reacts to a recognized speed limit. The predictive adjustment based on map data and the immediate reactive adjustment from the camera. The predictive function brakes gently because it knows the change before it's visible. The reactive function, however, acts spontaneously because it only reacts once the sign appears. This combination works accurately in normal situations, but when the camera misreads a sign or the map briefly supplies incorrect data, it can trigger a sudden deceleration or acceleration, especially if the adaptive cruise control or travel assist instantly adapts to the new limit. Such moments shape the driving experience more than every correct detection ever before them. A car that brakes unexpectedly doesn't violate logic. It violates trust. The engineers know this. That's why there are mechanisms to prevent extreme jumps. On motorways, for example, the system cannot reduce the speed like it wants, but only up to a certain amount. Still, in rare cases, for example, a temporary GPS or map error may cause the car to respond to a non-existing road segment. In practice, these events are rare. But when they happen, you remember them precisely. And yes, it happened to me too, from 120 kilometers on a Swiss motorway down to a sudden 50. That's why I personally think drivers should always have a brief reaction window before the new limit becomes active. 2 or 3 seconds, combined with a configurable, visible or acoustic warning, would neutralize many of these cases. But no matter how sophisticated the technology becomes, it remains an assistance system. No Škoda car as of today drives autonomously. Traffic sign recognition and adaptive cruise control support the driver. They don't make decisions. The driver remains fully responsible at all times. Hands belong on the steering wheel and the feet on the pedals. The hand detection system on the steering wheel, many find it annoying, is not a technical constraint but a safety barrier. It ensures that control and responsibility cannot be separated. A system can assist, but it cannot assume liability. The moral, ethical and legal implications of full autonomous driving will be a topic for another video. Also, traffic sign recognition is not a finished product. It's an ongoing process. Every improvement in the vehicle depends on data created outside of the vehicle, from map providers, public authorities and infrastructure. For me, the next logical step is called vehicle to X, direct communication between the car and its surroundings. A road sign that transmits its information digitally is the next logical step. The technology already exists and parts of the motorway infrastructure are prepared for it. But the digital foundation for everyday use is still missing, and it introduces new problems, such as potential attack scenarios on that very digital infrastructure. As long as this remains the case, traffic sign recognition will continue to be a system that represents an analog world in digital form, and therefore can never be complete. For partially automated driving, that is sufficient. For fully autonomous systems, it's not. They require high-precision maps, uniform standards, and infrastructure that actively communicates with the vehicles. But even then, the system remains dynamic. Every construction site, detour, or new route alters the data model. What is correct today may be outdated tomorrow. Perfection in this context is not a goal, but a temporary approximation, if you will. Technology can only reproduce the state of the world, never its next state. I know what you want to say right now, but however, I do not want to open a full discussion about the current state of autonomous driving in this video. Well, let's be clear. As of today, all available systems are far from what is defined as level 5 autonomous driving, where the principles I mentioned a moment ago would apply. As of today, with every system available, drivers must remain attentive and ready to take over control at any time. And essentially, there are two fundamental approaches right now: vision only and LiDAR radar supported systems. In other words, systems based solely on camera data, similar to how humans drive visually, or systems that combine cameras with LiDAR and layers of information. Tesla demonstrates what is technically achievable with a camera-only system, and it's awesome. Waymo, for example, shows what becomes possible when more sensors are added. But what they all have in common, however, is that they are digital systems that must navigate an analog world. And as long as this automotive world is built around us, around human beings, their mistakes and unpredictability, technology will have to live with uncertainty. Only when humans are no longer part of the system will that fundamentally change. Then the greatest source of uncertainty disappears, and with it, the reference on which current technology is based. That is when what we call autonomous driving will begin to take shape. And the consequences, technological, ethical, and economic, will deserve a video of their own. I hope this video has helped to show how complex traffic sign recognition really is, not only technically but also humanly. It was less about numbers and more about the interplay between statistics and perception, between behavior and trust. Because only when developers and users build a shared understanding, software can truly improve. If you're looking for practical guidance on how to use the assistance systems, by the way, like the road sign recognition combined with adaptive cruise control or travel assist in everyday driving, you can take a look at part 2 of my e-guide video here on the channel, where I cover the real-world applications. This video, part 1 here, focused on the fundamentals, the underlying logic behind the systems. So if you would like a dedicated in-depth video with practical demonstrations based on what we discussed here, you need to be a bit more patient. It's in the making and will come soon to this channel. And if the insight from this video was useful to you, I appreciate a like, a subscription, or a support of my channel in any way you like. Thanks for watching and see you next time. Stay full of energy.